Hi there. Today we're looking at more roots, more further maths, more looking at alpha, beta, gammas, I suppose, potentially. Also looking at this idea of which we've seen before, which is when you have a cubic equation, for instance, here. You'll notice there can be one root, there can be two roots, there can be three roots. When I say one root, I'm talking about distinct roots, one real root where it actually properly touches and crosses the x-axis. But you notice this one doesn't it? We've seen this before, and of course here when you get these complex roots. And we've also seen that when you get complex roots, they come in pairs, they come in conjugate pairs. So you always get 2 plus 1, of course, for here. We think of this as being 2 roots in one, really. They're repeated roots. We've talked about repeated factors for these. But these would be real. They are properly touching the x-axis. We'd call these repeated roots. And when you factorise them, you see that quite clearly. And these are just normal 3 roots. So we're going to be trying to find equations that give certain roots for certain types of either cubic, quadratic, quartic, whatever. So just a reminder, I suppose, the roots of polynomial equations. So for quadratics, we've already seen the sum is alpha plus beta is minus b over a, and the product is alpha beta, which is c over a. This is not new, this was seen last time. For cubics, we get the sum, we get the pairs and the product. Minus b over a, c over a, minus d over a. Notice the weird way of writing this, alpha beta plus beta gamma plus gamma alpha. So that's something to bear in mind. The typical way of writing it. And then for quartics, you get something slightly different, as much as you now get sums, pairs, triples and products. Again, you might not hear them called pairs and triples. This one might be called the sum of the pairs. This is the sum of the triples, I suppose. This is the product of all 4 roots. But notice minus b over a, c over a, minus d over a, and e over a. So that's something we've seen before. So if we are given the roots, we might be asked to find the simplest possible equation that would give you that root and those roots. I would just bear this in mind. It might be worth me just showing you this. So if this is my equation, then it might be y equals x minus 3, x plus 1. Now you notice that crosses at minus 1 there, it crosses at 3 here. And that's a nice little graph. It's not the only one though. All I would need to do is chuck out, say, a 2 or a 3 or let's say a 5, and it would still look broadly the same. Now the only difference actually would be if I was to do that, I'll just pick a different colour just so you can see the difference. It would still cross there, and it would still cross there, but 5 times by minus 3 by 1 would actually now cross it all the way down here at minus 15. It's not a very good graph, but you get the idea. And it would still do this. It would still have its line of symmetry in the same place. And it would still cross there, but it would just be a steeper version of the same graph. It's not a very good graph, but you get the idea. You see the line of symmetry is still the same. You see the roots are still the same. It's been stretched up and down, and because of that you've got 2 possible equations. Well, you've got an infinite number of equations which would give you these roots minus 1 and 3. So if you get given it the other way round, which is what I'm going to do with you, it just gives you a bit more to think about. So let me show you what I mean. So if you use the sum and the product or the roots to find the simplest quadratic equation. Notice I'm not meant to just factorise it and multiply out the brackets. So there's an easier way of doing it. So this is alpha equals 4 and beta equals minus 3. So I can do alpha plus beta. And alpha plus beta you can see is 1. I can do alpha beta, times them together. That equals minus 12. And notice this formula down here. This is the backward version of what we've seen so far. You know, where we've talked about the sum and the product being alpha beta minus alpha plus beta here, but it kind of ends up being slightly different. So as a result of this, I can just write, well, my equation must be x squared. What's my sum of my roots? That's 1. So it's always minus that. That's the one that changes its sign. Minus 1x plus the product, which is minus 12, plus a minus 12. Now you're not going to write it like that. You're going to write it at minus x minus 12. You can see, just tidy it up properly. But that's how you do it. Notice this. You won't be given this in the exam. This is something you're going to have to learn. X squared minus the sum of x plus the product equals 0. Now, is there another one? Yes, there is. This time it's alpha equals 6 and beta equals 5. So, sum them. Alpha plus beta equals 11. Multiply them. The product is 30. So we chuck into our equation x squared. It's always x squared at the front, on the quadratic at least, minus the sum. What was the sum? It was 11 minus 11x plus the product, 30, equals 0. And that's relatively easy. That's not hard at all, as long as you remember this formula. It's pretty easy to do. X squared minus the sum x plus the product equals 0. And it's always equals 0. You need to show that it equals 0. Now what is this, a cubic? Well, again, you could, I'll just do this one. You could write it's x minus 5, it's x plus 1, and it's x minus 2, and equal to 0. That's what we could do, but we're not going to want to do that. We're going to write instead alpha plus beta plus gamma. Let's find the sum. Let's do this sum here. What is the sum? Well, it's 5 minus 1 is 4. That's 6. Let's do the pairs. Now the pairs are alpha beta plus beta gamma plus gamma alpha. So, in your mind, assign them. That's it. I'm trying to remember what a gamma looks like. Something like that. There's my gamma on this. That's a gamma. So, let's times these together. We get minus 5. Let's times the 5 by the 2. I get 10. So, plus. In fact, I should do minus 1 times the 2, which is minus 2. And then I do 2 times by the 5, which is the 10. So what's that give me? I think that's 3. And my last one is the product, which is alpha beta gamma. And let's just times them all together. Minus 5, I think that's minus 10. Okay, so what's it give me? Well, again, as long as you remember, notice the way it goes. It just goes in the order that we found them before in our last PowerPoint. So it's x cubed minus the sum of x squared plus the pairs of x minus the product equals 0. So it's x cubed, and I know it's x cubed because it says it wants a cubic. Minus the sum. What was the sum? That was 6. X squared plus the pairs, that's 3. Minus the product, well, it's minus, so it's plus 10 equals 0. There it is. Pretty straightforward stuff as long as you know this equation for a cubic. Here's another one. Find the simplest cubic equation with roots 2 minus 1 and a third. Well, let's write it properly. Alpha is 2, beta is minus 1, and gamma is a third. So add them up. Alpha plus beta plus gamma. What's that? That's 1. That's 4 thirds. Now then I can do the sum. I've done, the pairs. So that's alpha beta plus beta gamma plus gamma alpha. So alpha beta, I think that, it's minus 2. Plus beta gamma, I think that's minus a third. And then third times 2 is 2 thirds. So that's a third. That's what have I written now? I didn't want to write. That's plus 2 thirds. Is that what I meant to write? Yeah, 2 thirds. So 2 thirds and minus a third is obviously plus a third. I think therefore that's minus 5 thirds. It's worth checking. You don't want to make dark mistakes on these things, do you? Then you want so negative 2 plus 2 thirds, and it's minus a third. So minus 5 thirds is right. So okay, we've got it all here, so I'm going to write x cubed minus the sum of x squared. Where's x squared? Oh, where's the sum rather? That was 4 thirds. So 4 thirds of x squared. And notice I put a minus in because you always do. Plus the pairs of x plus the pairs. This was this. I just realised I haven't finished this yet. Plus minus 5 thirds of x. I've still got to find alpha beta gamma. The product. Well, what's that? That's 2 times that is minus. 2 times by that is minus 2 thirds. And they've all ended up being this negative. These values with thirds in rather. So I've got to make it that negative minus a negative. That makes it positive 2 thirds equals 0. Now it does say the simplest cubic equation, and I don't think it's very simple when you've got all threes on the bottom. So times everything by 3 just to tidy up your equation. And I think the answer is going to be 3x cubed. That's the only one that's going to have a number in front of it, not changed, because, or rather it changed properly. And if I do minus 4/3 times by that, I just become minus 4x squared minus the 5x plus 2 equals 0. Just check in, yes, that's perfect. And obviously, I say this because we've done with cubics thing. I've just told you it's x cubed minus the sum of x squared plus the pairs of x minus the product equals 0. And up here, I've done the same thing for quartics. And quartics is x to the 4 minus the sum of x cubed plus the pairs x squared minus the triples x plus the product. Notice it just goes minus plus minus plus. This one goes minus. They all go minus plus minus plus. So just look out for that. Complex roots. Now, I've got to be able to deal with complex roots as well. I've seen these come up loads more recently on exam questions. So the quadratic equation 5x squared plus bx plus c. So they're hinting that this is the form of it, but really it's the same type of question. It's saying find the simplest equation. It just will happen to have a 5 at the front. So one of its roots is 4 plus 7i. What is it? It's a quadratic. All right. So when you know one root, and you know it's complex, you immediately know the other one. It's 4 minus 7i. So, okay, that's easy enough. Add them together. Alpha plus beta, this is the sum. Add them together, you get 8 in the real numbers, and obviously the imaginary numbers disappear. That's beautiful, isn't it? Just disappears. It starts off complex, but ends up being a real number. 8. I like that. Alpha beta, there I've got a times 4 plus 7i. By 4 minus 7i. Now you might spot it's the difference of two squares. If you do it, you get 4 4s are 16. Minus 28i plus 28i, they cancel. But the 7 times by the 7 is 49. I squared. Now, I could write minus 49i squared. But of course I squared is negative 1, so it just becomes that. And I think that makes it 65. And notice again, it is a nice real number which started off as complex and became real, and therefore my equation becomes x squared minus 8x plus 65 equals 0. On the face of it, that's done, apart from you go up here and it says no, I know that could be what the equation, but actually it's got 5 at the front, so that's got to be times by 5, and if that's times by 5, the whole lot's times by 5. What's that? 330? No, 325. Yeah, that's right. Equals 0. Let's see if that is minus 40, 325. I like that. Notice I've written out the equation. They say find the values of b and c. So technically I should write b equals minus 40 and c is 325.